Welcome back to The Explainer. Today, we're taking a structured look at one of the absolutely most profound questions in all of astrophysics. We're going to dive deep into the science and the leading cosmological theories behind the absolute outer limits of our cosmos. The whole concept of an ending point to reality, an actual edge, is something that completely challenges our baseline understanding of physics, mathematics, and even our place in the cosmic web. So let's get started.
You know, when you look up at the night sky, staring into that super dense canopy of stars and galaxies, your human brain automatically tries to map it using the rules of our earthly environment. It's totally natural to wonder if all this vastness eventually hits a hard boundary. Our intuition is heavily biased by Euclidean geometry, right? We evolved in a world where everything has a defined shape, a surface, and a definitive edge. A sudden drop-off, a physical wall, or a barrier where matter simply ceases to exist just makes logical sense to us. But as our source material points out, applying that earthly spatial intuition to the macrostructure of the cosmos leads us right into a trap. Space simply doesn't conform to the geometry of our everyday expectations.
Here's the thing. When cosmologists model the universe based on our current data, especially those incredibly detailed maps of the cosmic microwave background radiation from satellites like Planck, they aren't modeling a contained box. The prevailing data actually points toward a topology that is remarkably flat. And in cosmology, a flat universe stretches out in all directions as a never-ending, infinite expanse. I know, grasping the idea of a totally boundless manifold is incredibly counterintuitive, but establishing this framework is the absolutely crucial first step. We have to discard the idea of an encompassing boundary line to truly understand the mechanics at play out there in the deep dark.
Section 1. The Cosmic Boundary.
Defining a definitive edge essentially forces us to abandon the cosmological principle. And this principle is a massive foundational assumption of modern astrophysics. It basically states that on a large enough scale, the universe is both homogeneous and isotropic, meaning it looks the same everywhere and in every direction. If there's a boundary, well, that principle breaks down completely. An edge implies a center, it implies a gradient, and it implies a location where the fundamental laws of physics might just stop working entirely. If there's a boundary, what exists on the other side? More matter? A different physical vacuum? Just attempting to map a border completely shatters the standard model of Big Bang cosmology.
Moving on to Section 2. Measuring with light.
As you probably already know, mapping out the darkness requires us to think in terms of light years, because standard terrestrial measurements like miles or kilometers become mathematically meaningless at this scale. But a light year isn't just a measure of distance. It intrinsically links distance with look-back time. When astrophysicists study the extreme reaches of deep space phenomena, they are fundamentally studying the past. Measuring the volume of space requires us to map the space-time continuum itself, using the journey of photons across billions of years as our only truly reliable yardstick.
And the speed of light isn't just a velocity. It's the absolute speed limit for causality. It defines the maximum rate at which information, gravity, and physical interactions can actually propagate through the quantum vacuum. When we observe distant quasars or ancient galaxy clusters, we are entirely dependent on this single constant. It's the inescapable governor of reality. We literally cannot interact with or measure anything that exists outside the causal framework dictated by the speed of light.
So, by combining these observational tools with strict mathematical models constrained by the speed of light, scientists construct the lambda-CDM model, which is the prevailing framework of astrophysics today. Measuring distances across spacetime, tracking the distribution of distant matter, building sophisticated topological models, and anchoring all of it to the causal limit of light speed allows us to really piece together the universe's true scale. But even with this highly reliable scientific foundation, astrophysics faces a major complication that shifts our entire perspective.
Which brings us to Section 3, the expanding universe.
The universe is not a static stage where celestial events just play out. It's actively undergoing metric expansion. So matter exists in space, yes, but the actual space between that matter is continuously stretching, which means any theoretical cosmic boundaries are perpetually moving further outward. And we aren't talking about galaxies traveling through space like projectiles from an explosion. It's the underlying metric of spacetime itself that's expanding. The scale factor of the universe is increasing everywhere, all at once. Because space itself is literally generating more space, an expanding boundary means the edge is a completely moving target. The distance between any two non-gravitationally bound objects just increases over time. This dynamic stretching means that defining a fixed edge is theoretically impossible based on our current understanding of dark energy and cosmic acceleration. You simply cannot map a static boundary in a manifold where the geometry itself is inflating.
The horizon isn't just far away, the distance to it is compounding exponentially.
Section 4. The ultimate speed limit. Okay, there is a profound paradox at play here when we look at the physics of observation. General relativity dictates that nothing can travel through space faster than light. That's our absolute cosmic limit for observing distant matter. However, space itself is not bound by this rule. The continuous physical growth of the universe, the stretching of the cosmic fabric, can and absolutely does happen at a rate that exceeds the speed of light. This superluminal expansion creates a massive rift between what actually exists and what we actually observe.
Because our practical experiments and observations are tethered to that causal speed limit, they can only reach so far. This creates the observable universe, a massive spherical region from which light has had enough time to reach Earth since the Big Bang, roughly 13.8 billion years ago. Now, due to cosmic expansion, the current proper distance to the edge of this observable sphere is about 46.5 billion light-years in any direction, making the whole diameter 93 billion light-years across. That's huge. But because the universe expands faster than light, there are regions of space constantly slipping past our cosmic event horizon. Their light will literally never reach us.
Finally, Section 5, an infinite mystery.
So let's compare our observations to reality. Our observable universe, our specific Hubble volume, is ultimately just a local bubble within a much larger and potentially infinite reality. What we can measure, test, and map is entirely bottlenecked by the speed of light and the age of the cosmos. The true global universe mathematically extends far beyond our 93 billion light-year sphere. It's an expanse that permanently hides its true nature and any theoretical boundaries behind this veil of superluminal cosmic expansion.
This leaves us staring into the cosmic abyss with a truly staggering final thought to wrap up today's explainer. If the physical reality of the universe's metric expansion outpaces the very light we use to observe it, the edge isn't just incredibly distant, it's fundamentally unobservable. The galaxies pushed beyond our cosmic event horizon are forever lost to our science. Are we, and any future civilizations, destined to only ever know a shrinking fracture of the cosmos? It's a huge reality to grapple with, and one that challenges us to keep pushing the boundaries of theoretical physics to understand our place in this expanding dark. Keep questioning what lies beyond.